Alright, in this lesson we are learning to factorize a degree 3 polynomial. The question says factorize over c. That means we need to find all of the factors, some of which may be complex numbers. Now the important thing to remember here is that since it's a degree 3 polynomial, we should be able to find 3 factors. You remember all of the quadratic polynomials we were doing? Quadratics have a power of 2, a degree 2, and for all of them we found 2 factors. So degree 3, in this case, we should be able to find 3 factors. Now we're going to combine a few of the different techniques we've learnt along the way in the last few lessons. In order to do this, to find our first factor, we actually need to guess our first factor. Now we may not guess correctly, and this is how we guess. We're relying on factor theorem, if you remember. Factor theorem was that if p of a equals 0, then z minus a factor. Okay, that's what we're relying on. So let's try. We don't know what any factors here are. Okay, it's a bit of a complicated thing to try and be able to see a factor. Cross method won't work. You know, we can't do this because it's a cubic. It's a degree 3 polynomial. It's not just a quadratic. So we actually guess. We try p of 1. And we actually say try p of 1. And we sub 1 in and we'll get 1 minus 4 plus 2 plus 28. Does that equal 0? No, I don't even need to work it out exactly. I know it can't possibly equal to 0. Try negative 1. Remember, what I'm trying to do is get something, guess a value of a that gives me 0. So p of negative 1. Negative 1 cubed is negative 1. Take away 4, take away 2, plus 28. Clearly still not 0. Let's try p of 2. P of 2, well, 2 cubed, 8, minus 4 lots of 2 squared. 2 squared is 4 times negative 4, minus 16, plus 2 2s are 4, plus 28. I can see that that is not going to be equal to 0. What about p of negative 2? Hope we get it soon. P of negative 2 will be negative 8. Negative 2 squared is positive 4, times by the negative 4, still negative 16. 2 times negative 2 is negative 4, plus 28. Aha! That equals 0. We've just found that p of negative 2 equals 0. Therefore, since p of negative 2 equals 0, then z minus negative 2, a factor, or that is z plus 2, a factor. Therefore, what we've just found then, go back to that fundamental theorem of algebra, is that p of z, this original polynomial, I've now found one factor. I've found that z plus 2 is a factor. We know that altogether there should be 3 factors. So we've got 2 more factors to find. We could try and keep guessing, but we're only guessing real numbers. What if the other 2 factors are complex? And I want to remind you of something here. Notice that all of these coefficients are real. So since all the coefficients are real, if there are any other complex factors, they will occur in conjugate pairs. But at the moment I don't know what this other factor is going to be, or these other two factors are. But I do know that this is a cubic, and I've found a linear factor. Linear means just a power of 1. So P of z must be equal to this factor multiplied by something else. What would this something else be? I don't know exactly, but I do know I can see some of it by inspection. Because if I expand out whatever I write here, I've got to get this. So z multiplied by what would give us a z cubed? That has to be a z squared. That's the only way that I can multiply anything out here and get a z cubed. The other thing is I know that my constant term, the 28, has to come from the 2 multiplied by something here. So 2 times what gives you 28? You know it's got to be a plus 14. So those two have to multiply to give that, you know that, and the 2 times this has to give you this. All this other stuff in between can be made up of combinations of this expansion. So I know I've got a z squared, I know I've got a constant, I'm also going to need a z term, but I don't know the coefficient of the z term, so I'm just going to make it a p. Now our goal is to find the p. Once we find the p, then we've got a quadratic here that we can factorize into 2 factors. Once we know what the 2 factors here are, we'll have all 3 factors for the whole polynomial. We'll have this one and 2 from there. So our goal now, what I'm going to be working on now, is finding that p. So to do that, we actually expand this again. We'll expand this and we'll get z times z squared will be z cubed. Z times pz will be pz squared. Z times 14 will be 14z. Now the 2z squared plus 2pz plus 28. So sure enough, we got the 28 at the end and we got the z cubed at the beginning. But all these other bits in between help make up these other terms. So now we collect our like terms. We've got z cubed. Now let's collect all our z squareds. And I'm going to take z squared out as a common factor. I've got p, lots of z squared, and I've actually also got a plus 2. And now I'm going to take out my z as a common factor. I've got 14 of them plus 2p of them. And that does that, and then plus my 28. Now this, it says, is pz. So this here must be equivalent to here, because they're both pz. So sure enough, the z cubes are the same. Therefore, equating coefficients. Our z cubes are the same, therefore our z squareds should be the same. Therefore, p plus 2 is like my coefficient. I know I've got it written afterwards, but it wouldn't matter whether I wrote that p plus 2 in front or not. P plus 2 is the number in front of the z squared, the coefficient of the z squared. The coefficient of the z squared up here was -4. So p plus 2 must be equal to -4, which would give me p equals -6. Oh, that's what I wanted. Let's just check what happens over here. What if I equated my z coefficients? My z coefficient here is 14 plus 2p. My z coefficient up here is 2. Okay, I'm just equating my coefficients because these two polynomials are both pz, so numerically they must be the same. So rearranging this, 2p will equal negative 12. P will equal negative 6. So I didn't even need to do this, but look at that, it's consistent. It's lucky it is. If it wasn't, I would have made a mistake. So what I've worked out is that P is equal to negative 6. Therefore, PZ equals Z plus 2, the factor that I'd guessed, multiplied by Z squared minus 6Z, because P was negative 6, plus 14. So now I need to factorize this, my quadratic. Now factorizing quadratics, you might say, let's just go to cross method. Alright, let's try it. Z and Z. Factors of 14, 7 and 2. If you look at it, you'll get 2z, 7z, it's going to give you a 9z. No, that's not what we wanted. Maybe they're both negative. No, that will just give us negative 9z. In fact, there's no cross method that will work for this. So this is where the completing the square lessons that we learnt come in handy. So let's turn over. So let's take, what we'll do is we'll say take, put that one there, z squared minus 6z plus 14 and complete the square. So z squared minus 6z, the coefficients, the coefficient of the z is 1, so that's good, we can keep going, we don't need to take out any common factors. We take this negative 6, we halve it, will give us negative 3, we square it, we get 9. We can't just go adding 9, we've got to get rid of 9. And then don't forget, the question actually had the 14. But this is what we're going to group together, and this is what we're going to group together. Equals z squared minus 6z plus 9 minus 9 plus 14 is plus 5. Now this bit, remember, is what we're grouping. It becomes z, it becomes your perfect square. The number here is whatever we got when we halved the coefficient of negative 6, the coefficient of z, when we halved the negative 6. So we got negative 3. Check. First term squared? Yes. Twice the product? That'd be 3z times 2 is 6z, or negative 6z. Second term squared, positive 9, yes, plus 5. We want to factorize this. So we force it into becoming a difference of 2 squares. So it's really now an a squared minus a b squared equals a minus b. B is the square root of this, so the square root of 5 is root 5, and square root of I squared is just I, and then a plus b. So what we've done is we've shown that that quadratic is now factorized into 2 factors, this times this. Therefore, PZ, our original polynomial, is equal to z plus 2, the factor that we guessed, multiplied by this quadratic, but that quadratic is this, z minus 3 minus root 5i, z minus 3 plus root 5i. Now notice here, these are our complex factors. Do they occur in conjugate pairs? Absolutely. One's a minus root 5i, one's a plus root 5i. The reason they occur in conjugate pairs is because the coefficients in our original polynomial were real. And so there is our final factorized polynomial. Notice how many factors we've got. 1, 2, 3 factors. It was a degree 3 polynomial, therefore we should have got 3 factors, which we did.